Institute. Today's Introduction to Algorithms video is going to cover an introduction to binary search trees. We're going to kind of redo these trees in kind of the future, but for now we want to start talking about some of the properties they have and see how those kind of apply and can be implemented using the class, right, the tree class, binary tree class we've already kind of seen in the previous video. So we're going to be building on that class to remind ourselves what the different methods and stuff we had there were. Right, this was pretty basic. We had the binary tree, creating a new binary tree with a given root value. We inserted stuff to the left or to the right. Remember, these were always binary trees, right? So they had at most 2 children for any node. We could get the left child, get the right child, and set or get the root value that way as well. Now, we actually won't even need all of these things, which is one of the reasons kind of when we revisit this in future videos, we'll kind of start and do these things in a slightly different manner, right? Really here, when we're going to be talking about a binary search tree, we want that to be its own class. We want to kind of build that from scratch. But as far as the basic properties and some basic operations, we can see how those could be implemented or could be thought of just using our basic binary tree here. So before we can be talking about binary search trees and things like that, we need to know what they are, right? So we better start with kind of saying, what is this kind of idea? And the idea actually comes into kind of a property. So really when we're talking about a binary search tree, this is really a shorthand way of saying this is a tree, a binary tree, with the BST property. So what is this property? The property is that, right, and this should remind you of binary search. That's where the name comes from, right? The idea here is all of the values in the left subtree are less than the root. All of the values in the right subtree are greater than the root, right? So we have some kind of root value here. So if we have a tree and we have kind of a value r at the top here, right? So that would be kind of our top root value in this case. As far as our subtrees then, right, we could have kind of a left subtree and a right subtree, and these would be divided into values all less than r and all values greater than r. So this kind of is the generic structure of this binary search tree property. We always have this in a binary search tree, right? So some trees might have this property, some trees might not have this property, but a tree, and in particular a binary tree having this property, is what we would refer to as a binary search tree. So you can probably guess some of the advantages of this, but just to kind of think about this here as far as some examples, right? What does a binary search tree with these following kind of values look like? So you might kind of think of this and say, okay, what's my number in the center? We have 70 in the center. And then, right, I could actually do this in a pretty nice way here. So we could have 70, we could have 23 as its left child, and then notice from 23, we could go to kind of 14 for 31. And then kind of from there, right, maybe I say 93 on this side, and then we have our 73 and 94 here. So let me just shrink this up a little bit, just so we can kind of see this all a little bit easier in this case. So if we shrink this up, here we have kind of an example of a binary search tree. Now, one caution here, right? What does a binary search tree look like? Let me highlight this A there. There's not a specific answer. So one of the things that's a little bit weird here, or it takes maybe a little bit of getting used to, is that you can have different binary search trees with the same values, right? And this will be something we talk about more in future videos. This is where some problems come in, right? So maybe we have another binary search tree that has 23, and then we kind of branch to 14, and then we maybe branch to 70. We have kind of 31, then maybe we have 93, and kind of 73 and 94. So, right, this still satisfies the property, right? If I look at all of the values in the right subtree, they're all bigger than 23. All of our values in the left subtree are smaller, right? So this kind of works as well. These are both valid examples in this case. So we want to kind of be careful here that these BSTs don't need to be unique, right? So So they could have the same values, but maybe in different arrangements here. So this is one kind of caution we want to kind of be thinking about. Another thing to kind of think about, I think we can agree, even if we don't have details right now, probably the green tree is somehow like better than the blue tree, right? It's maybe more efficient. The height of the green tree is 2. The height of the blue tree is 3, right? So we have different ones. They don't even have to have the same heights. You can probably picture how we can even do worse. It's definitely possible to do worse than the blue tree. And that's something definitely we're going to talk about more when we really think about other operations and how we maybe want to be a little bit careful when we're doing these kind of operations on a binary search tree. So that's kind of our goal and kind of idea in this case. So let me keep one of these around here for a second. So let me keep the blue one around. It doesn't really matter which, but the blue one kind of will fit better with my next slide, I think, anyway. So suppose we want to, or we have a binary search tree. Remember, these things aren't necessarily unique. So as long as we just have a binary search tree, we want to ask ourselves, can we use that to our advantage for kind of efficiently checking for a value or efficiently searching for a value and stuff here? Now, the name binary search should help ring some bells, right? When we did binary search on a sorted list, what was the idea? Well, you look in the middle, right? And if it's bigger, you look at the one half. If it's smaller, you look at the other half here, right? So comparing this to binary search, what is our kind of middle? Our middle is the root, right? So the root is where we kind of start kind of looking, right? So the whole thing here, this should really make sense with what the binary search tree property is. The property guarantees that if I look at 23, right, now all of the values smaller than 23 in our tree are to the left. All of the values that are larger are to the right. So just depending on that 23, right, we can cross out or get rid of half of the list, right? Or sorry, half of the tree. And by half, this is where some of these problems that I mentioned before, we want to start thinking about, right? So it's not actually half, right? The right subtree has more nodes than the left subtree. And those are some of the things we want to kind of worry about a little bit more in the future. But, right, you check at 23, right? Maybe it's less than 23. So then we can kind of scribble out all of this stuff, and we only focus on the right subtree there. So those are some of the kind of things we can do when we're talking about efficiently looking for a value. Now, actual code here. So remember, we had this binary tree class. So let's look at some code here that can work on one of those trees. Note, this is not a method. I'm not defining this as a method for that class, right? This is a function that takes in the value of the tree. So our two inputs are the tree itself, as well as the value that we're looking for. So the value here is the one we're kind of looking for at this point. So where are you looking for the value? What's the tree? And then what value is it that we're looking for? And this is, right, I stressed over and over and over in our binary tree class, everything can be thought of kind of recursively. So if we have an empty tree, or if our tree is none, is our value in it? Definitely not, right? So if we have a none value, we return false. Otherwise, we look at the root value of our tree, right? So the root value here is kind of what we're looking for here. So we would get to that kind of 23 in this case. So, right, not only is this not a method, I'm kind of doing the debug version of this kind of search tree as well, right? So if you wanted to look at this code, it would print out at this point, right? That root value kind of is working there. And so if we kind of step through this, that'll kind of help you see what's happening in this case. If the values match, if this root value is what we're looking for, we're done, right? We print out true, right? We found our value that we're looking for here. If the value we're looking for is to the left, right, or smaller, right, then we can do a pure recursive call here, right? So we call our same function with the left child. Remember, that left child itself is a subtree. So that's why this works, right? Our left child there actually is a subtree. So we can call this same function on the left side. Or we call it on the right side in this case. So, right, just as an example here, right? So just to do kind of a quick example at the bottom, right? So if we, for example, look at, right, what's going to happen if we do BST on this search, right, B, and let's say we search for 72. So this will be kind of one that's definitely not in our list, right? But kind of what happens here. So we're going to start looking here, right? So let me kind of get rid of some of these highlighted things. We're going to, of course, look at the top. So it will print out that 23, right? So this is where I want this kind of print value in here so we can kind of step through stuff there. It's going to look, okay, we have 72. That is definitely larger than 23. So we then move on to the right subtree here. So now we're working at the right subtree in this case. So next, it's going to print, after printing 23, it will now print 70, because now we're there. We're still larger than that. So we look and find 93, right? So we kind of print the 93 in this case. Now we're smaller than that. So we go to the left. So now we're going to print 73. We're smaller than 73. So we go to the left. Now, remember, there's nothing drawn here on my graph, but what is there? Remember, officially, there is a none. Whenever we create this tree, it has the root value. The left child is none. The right child is none. So we're going to call this then at none. And so at this point, we will return false. Right? So that kind of is the steps of doing this as far as Python is concerned. Right? We can search through one by one the different portions of this tree. And then once we either find our value, which has to be one of those, will eventually be one of the root values, because that's the only thing our kind of binary tree lets us look at as far as values are concerned. Either we find that or we get to a leaf, so the child and right and left childs are none, and then we return false. So that's kind of where we're going to step through this here. We'll talk more about efficiency and stuff like that here, but it should be pretty clear that this efficiency depends on the height, right? Every time we do this recursive call, we step one level down in our original tree, right? Every time we do a child, the height of that child is smaller than the height of the original tree. So that's where we're kind of working our way down until we kind of have our final value in this case. Okay, so how does this work then? And so this, again, can maybe get a little bit more complicated depending on what you want to worry about or what you kind of want to kind of check with things and stuff there, right? What if we want to add a value the same way? Well, this should not be too surprising that this is very, very close to the previous example, right? So the previous example, we looked at 72, right? So 72, we said, oh, it's bigger than 23. It's bigger than 70. So we move on to the right again. It's smaller than 93, so we move to the left. It's smaller than 73, so we move to the left. Well, wait a second. Instead of kind of getting to the point here where we have a none value, if we do this kind of same procedure, by the time we get to the end, that is a place where we need to just add the value in, right? Where we got to a place where we had a none value, but then instead of that none, we want to kind of say, okay, we should have our tree actually be modified in that case. So what does that kind of mean then as far as an implementation? And again, this is pretty straightforward here. And you want to think about this as similar to the kind of previous one there, right? The whole kind of point here is that we're kind of stepping our way through the kind of tree that way as well, right? So we go to these kind of different portions, right? We say, okay, are you bigger? Are you smaller, right? And then we're kind of modifying the tree in the same recursive manner as before, right? Our ending spot here, right? Our ending point instead now is, right, setting a new tree in that case. So in this example, by the time we got back to this bottom portion, right, we were looking at the left child of 73, right? So the left child of 73 was our value. And then, right, we're adding that value here of 72. So same type of thing in this case. So you step through, I'm just returning true. You might ask, what is this step here where we return true? Well, let's just pretend in this example at least, we don't want repeated values. So this is just saying, oh, if your value's already there, you don't need to modify the tree at all. So we kind of just return true, we return that it's already in the tree. Otherwise, we keep stepping through, going to the left or the right, until we kind of get to a none, which means that's a place where we can put in our value. That's an empty spot in a sense. So we put in the value at that point. Again, keeping with this recursive structure, right? Keeping with the fact that this is still another binary tree at the end. Of course, its children, when it's just created, are empty, but that's how we kind of build the property in from there. To be clear, this is still assuming that we started with a binary tree that had the BST property. This function will preserve the property, right? We're modifying the tree. We're keeping it in the kind of, we're keeping it a binary search tree. We're keeping it satisfying this property if it did at the beginning, but we're making no guarantees of what happens if we started this with a random tree that wasn't a binary search tree, right? This doesn't really make as much sense in that case. Okay, So, like I said, this video was just kind of an introduction. This one's a little bit of a shorter video here, right? This is meant to do an introduction to binary search trees, getting us to think about the property. What does it mean to be a binary search tree? And I want us to start thinking about the advantages of keeping a tree organized in this way. And then in the future, we'll keep expanding on these properties. Like I said, it really makes sense to build this kind of binary search tree from scratch if we're really going to make it an object, we're really going to make it a class we want to be working with. So we'll kind of go back to some of our nodes and things like that as well. But this is just an intro, and these kind of algorithms, the recursive way of doing this, will be very helpful to keep